So what I want to show you guys today is the execution and task planning mechanism that we've been building to allow agents to request from the protocol and the registry work to be executed on their behalf, or by users through various applications to do exactly the same thing. But I'll also tying back to the thread that I was making a couple of weeks back regarding Google's agent-to-agent protocol, and where I kind of brought up some controversial points mentioning that agents could, in theory, actually collaborate through MCP alone. So what we'll be looking at is solving a composition or a composed task, which is a multi-step process of dependent tasks to do, which in this case is simple mathematics, just because it's easy to verify, it's easy to calculate, and it's perfect for demonstrations. And the problem that we'll be looking to solve is 5 plus 3 minus 2 times 2, which is equal to 8 minus 4, which should equal to 4. And this is a representation of how you would call that in the protocol, or have an agent call it for you. That's what we are currently testing on as well, but more of that will come in the very, very near future. And it follows a lot of the principles and premises of MCP already. We have an ID of the agent to execute the task for the registry. We have the operation, which is basically a combination of the capability, which is a tool, a resource, a prompt, or whatever, and the actual method. And then we have the arguments that we pass into it. If you have a multi-step process, you also need to define parent, because that basically says, hey, don't execute this task until you have the results from the parent tasks. And that's what we're doing here by taking 5 plus 3 and 2 times 2 and plugging that into the parameters of the last step that we're looking to execute. And what that effectively will look like is that we'll fire this off. You'll see that we have a unique task with the UUID and a pending state. Now, if we actually look to get the status of this task, we can read from the API as well. It just gives a snapshot of where we're at right now. And we are in a pending state. The representation of this task is the final task, which is known as the root or the leaf, depending on how you look at how the structure is being made. The interesting part is when we actually execute this thing. And the way we do that is we call the execute endpoint, which effectively will just trigger the first tasks that are waiting that can be executed, and then step by step actually feed through this output and plug that into the next step. And hopefully at the end of it, we should have some form of output. So if we look here, we did the first 2 steps in parallel. We got some output, and then we got some more. Here you see the step that we are looking to execute as the main task. And we saw that it actually outputted a value. The result shows the value 4. But just to verify, let's get the state of the task again. And here we can see that the same task that we got before has now executed the final subtraction, and it basically took the input of 8 and 4, which was the expected outputs of the addition and the multiplication. And the result was to subtract A from B, and that gave us 4. Now, as we saw, like mathematics to this level is quite simple, quite straightforward. It doesn't necessarily change the world by just doing this, but the core premise of all this is that this can be any arbitrary task. And a task here is just some form of tool with input through MCP, and then the output is being parsed, converted into what matches the expected input of the following task to then effectively give us some form of output. And that can be an agent, an MCP server, and then the world is your oyster.